Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. We are going to talk about another sin here, ozonolysis, ozone addition to alkenes. What does that mean? Ozonolysis. That means we're going to take ozone, yes, the same ozone which is up in your ozone layer. We kind of create it in the lab. We have an ozonator. And then we put that on a double bond and literally cleave this bond. Pi and sigma. This and the KMnO4 hot are the two reactions here that actually cleaves the entire pi bond, pi and sigma bonds. So this is one of the few reactions that's very, very reactive. You might even say corrosive because it really chews up your bonds. Ozonolysis. Lysis is just hydrolysis where you break up a bond. All right, let's go. Let's see what this looks like. First of all, let's look at ozone. You've seen this in Gen Chem. Just to bring it home again, well, ozone is 18 electrons. So if you take ozone, you're putting, well, all three are the same. So you put one of them in the middle. That's 4. There's 14 left. And 6 and 6, that's 12. So you got 2 left. You put it on the central atom. Obviously, you don't have an octet here. So you move this over here and you will get a pi. So doing formal charges on this is 0, this is a +1, and this is a -1. Obviously, you can have a lot of resonance, which is why ozone is a very stable molecule for the most part. So here is your ozone resonance. This is kind of a classical example of resonance. And you can see because you have a positive and a negative in this molecule, you can have an electrophilic oxygen and a nucleophilic oxygen. Does that matter? In this case, this is going to act as your electrophile initially, and your pi bond is going to act as your nucleophile. So here we have a pi bond. Let's name it for good practice. So where do you start numbering? 1, 2, 3, 1, 2, 3. Obviously, this has more lookout points or branching, so we're going to go in this direction, 1, 2, 3, and give the lowest number to the alkene that way. And it's going to be a hexene with 2 and 3 being dimethyl. But we also have an asymmetry here, and you will have E and Z. In this case, this is higher priority, and here this is higher priority. So this is a trans or an E double bond. And since there's going to be an alkene on the 3 position, you would call this a 2,3 dimethyl hex 3-ene or 3-hexene. You can even put a 3E here. All right, let's look at the reactions. We are going to have a pi bond sitting right here, and we are going to have an isopropyl on this side, a hydrogen here, and a ethyl going back. So that is your geometry at the beginning. You can have your ozone add on top, or you can have it add at the bottom. It's just a pi bond. So let's say this is your pi bond here. You can have your ozone coming from the top or coming from the bottom. Both oxygens are going to go in the same direction. So it's syn stereospecific. Syn stereospecific, no way this can wrap around and go one up and one down. It's impossible geometrically. So it's going to be syn and more syn. All right, let's draw it out. So same storyline as before. Nucleophile, attack electrophile. Here's your electrophilic oxygen way up here. And we got to get our electrons all the way there. So these 2 electrons are going to swing over and move it over into your oxygen. And it could happen with this as well. This pi moves over, and now that you've lost electrons at this end, it's going to be positive. So that's going to pull those electrons down. Now, it can also happen underneath this, from below this molecule. So you can have above and below. And as we've seen before, I'm just going to run with this. In this case, you're going to lyse the bond. So eventually, you're not going to see any of the stereospecificity. But the initial start is very stereospecific. It can only go in one direction. So therefore, you are going to have, let's draw the transition state, a transition state here with your oxygen breaking up the pi bond to go over here. And then that oxygen is going to grab that incipient positive that's forming over here. So now this is your transition state, and you would get, well, attack from below. So you will get enantiomers, and you're going to then gel the bonds in place. And well, these sigma bonds are going to be right here, and for right now, and you are forming a new sigma bond here, and the pi bond's gone, and a new sigma bond here. So you pretty much broke two of these pi bonds and formed two sigma bonds here. Now all of these are going to be neutral. This is a molozanoid. It's not there for too long, because when you have a lot of oxygens like this, it's really high energy, unstable, explosive even. So you are going to kind of tear apart these bonds. Well, you got to start somewhere. Let's start over here. Well, as you can see, they're tugging on these bonds. So this is going to then come down here, and that's when the pi bond is going to pop. Now that's going to be too many bonds for this. The oxygen then moves over to the top. Next is a intermediate or two intermediates, two molecules here. Okay, so following your arrows here, you're making an sp2. So this is going to be a double bond over here. And that's got a hydrogen and an ethyl. Now this is sp2. So that's flat. This carbon over here is going to have a double bond and an oxygen right here. This oxygen has moved over here. You lost a lone pair, and so you're positive here. And when this moves over, you have three lone pairs here. That's a negative. So here is a situation where you have two molecules. These are called creepy intermediates. Now, these intermediates will instantly rearrange. So again, this is going to then, I'm going to put this in a different color. This is going to go over here. These pi bonds are then going to go over here and move this to that electrophilic oxygen. Now you're going to get a ozanoid. So your ozanoid is going to have a house. It's almost like it broke up one house and it's creating another house. That's pretty much the story here. So this house is now kind of a upside down house. So you broke up two pi bonds and you made two sigma bonds. And here are your lone pairs here. This is your ozanoid. Well, ozanoid kind of moves along. It looks almost like a spider. And this is then going to kind of come apart. So you have in your solution DMS. DMS is dimethyl sulfide. It's almost like an ether, except it's got a sulfur instead of an oxygen in the middle. Now, this is very electron rich. This is electron deficient because oxygens are kind of pulling those electrons in all directions. This is electronegative. So your sulfur here is going to donate electrons into this electron deficient oxygen, Well, there's too many for that to handle. It's going to push those electrons over here, which is going to push these electrons over here, breaking up that ozonoid all over again. So you build a house, break it up. Build a house, break it up. That's pretty much the storyline here for ozonolysis. Lysis, breaking up. That's what they do best. All right, now that it's got over here, that's too many here. These bonds then step out. I mean, you can go over here and give the lone pair, or you can draw it straight to the sulfur. Let's look at this for a minute. You're going to have a double bond forming here, and this is breaking up. So this is going to become an aldehyde. You're going to have a double bond form here, and you're breaking this up. And so this double bond's got two R group. That's going to be a ketone. This oxygen is going to be taken over and carried away with this sulfur DMS. It's almost like a stork that swoops in, picks it up, and runs away. So you're left with two groups here. So you would have this with an oxygen, aldehyde, plus you would have this here with a ketone. So it's basically breaking up that entire pi and sigma bond. So you have a lysis here with ozone, which is why we call it ozonolysis. Your DMS, which is dimethyl sulfide, is going to pick up that oxygen now. So you have a sulfur and you have a sulfur that's connected to that oxygen that was actually part of the ozone. So you have one oxygen here, one oxygen here, one oxygen here, all three oxygens in three different houses by the time this is done. This, I think you remember what it is, and I hope you do, is your DMSO, your SN2 solvent for aprotic backside attack. Remember that? Popped up again. So here's your DMSO, here's your aldehyde, and here's your ketone. Now, there's no stereospecificity shown in the products. The stereospecificity is here, where you only have attack on one side above, plus below. So I'll put attack above and below pi bonds. So that is syn stereospecific. Now it goes the same amount on both ends, so it's not stereoselective. And even if it were, it wouldn't matter because we're breaking it all up. All of this really doesn't matter. So it's non-stereoselective. It goes same amount on both carbons. And it's non-regioselective because there's no way you can choose one end over some other end. It's going to go plop above and bam below. So it goes on both sides equally. So it's non-regiospecific. There's no Markovnikov, anti-Markovnik, none of that nonsense here. It's non-regioselective, syn stereospecific, non-stereoselective. Initially, it's syn stereospecific, but we break it all up anyway. So what does it really matter? Just for mechanistic reasons, we call that a syn addition. Now, what if you had all of this in an aqueous or protic environment? You're going to oxidize this further to carboxylic acids. Now, I've done an example with an open chain. If you had this, let's say, in a ring form, and six-membered rings are the most common, so, well, why don't we just do that? So here, whenever you see this, and you see ozone, O3 DMS, just put a line right through the middle. Put one oxygen on one side, put the other oxygen on the other side. That's it. All right. And just open it up. So you're breaking your pi first and your sigma. So this is breaks sigma. That's major. You're breaking a leg here. You're literally changing the whole anatomy of this molecule. The backbone's gone. So you're opening it up to two different molecules. Here, it's a bit different. You put them right here and cleave that sigma and pi. Let's draw it out just the way it is. And you can see 6-membered ring here. And you have a double bond here and a double bond here. The stalk removes the third oxygen. And well, this is kind of drawn in a curled up position. You can open it up and you can have your ketone on this side. And you have 1, 2, 3, 4 carbons in between. And you'll have your aldehyde on this end. So that's one of the things that you can get. And if you have different numbers of carbons here, you'll have different numbers of carbons here, but what happens to the alkene remains the same in the presence of DMS. And it's got to be free. It's got to be really, really cold for you to do this. Or if you have water here, this is going to go oxidize to carboxylic acid. All right. All right, just a few notes. I mean, if it gets a little overwhelming, just remember a few things. One, start with the correct Lewis structure of ozone. That's key. Once you have your transition state and you make an intermediate, you start with one of the lone pairs going in here and breaking up that pi bond and making a double bond here. Move this over and you will have a negative. The second time around, start with the negative attacking this and then going over here and pushing those electrons to the positive. And make sure that you draw this spider kind of thing. And once you've done the ozonide, bring the DMS and pick up one of the oxygens. So once you do that, that sigma bond's going to have to make a pi bond here, and that sigma bond's got to make a pi bond here. So I hope that helps. But whatever I may say, when your pen hits that paper, it's only what you practice that's going to come out. Okay, so just make some flashcards. I'm sure it'll be fine after a few times. All right. Anytime you have questions, let me know. Again, one more thing. If these are tethered together like this, you only get one product. If they're open chain, you will get 2 products. Talk to you soon, guys. Practice, practice, practice. Bye.